Hello and good evening. I hope that everybody can hear me. Welcome to the fourth Seven Pines public lecture. My name is Jos Uffink and I am the chair of the Scientific Advisory Board for Seven Pines. So what I would like to do today is first of all tell you a few words about the Seven Pines initiative, and then introduce our speaker for today, Professor Peter Galison. The initiative for Seven Pines Symposia was taken by Lee and Carlotta Kalicki, who are passionately interested in the achievements of modern physics and their philosophical and historical implications, and also own a mansion in Stillwater, Minnesota. About 25 years ago, they got together with Roger Stewart, who is a professor in the history of physics at the time at the University of Minnesota, to launch this initiative of the Seven Pines Symposia, which are dedicated to bring together leading historians, philosophers, and scientists to probe and clarify significant foundational issues in science. This tradition has been carried on throughout the years, and this coming week, we will have the 24th Seven Pines Symposium. I should say that this tradition of the Seven Pines Symposia has been an enormous success. Over the years, these symposia have attracted at least 6 Nobel laureates. Many of them have come more than once, as well as many prominent scientists, philosophers, and historians. And also, there's always also been room for some young career scholars and some graduate students. But part of the success of this Seven Pines tradition is that it's really a selective group of people that get together in a secluded mansion out there in the woods around Stillwater. So it's something that is not very well known to the public. And in fact, I often said it's Minnesota's best kept secret. A couple of years ago, the scientific board decided that we should enlarge this initiative of the Seven Pines Symposia by also including public lectures, of which this is the 4th. And so I'm welcoming you all to this free public lecture associated with the Seven Pines Symposium, but contrary to the symposium, this one is accessible for all. So let me now say a few words about our speaker, Professor Peter Galison. Professor Galison is a prominent and quite accomplished philosopher and historian of physics at Harvard University, where he holds the Joseph Pellegrino University professorship. He has written numerous books and papers focusing on topics like how scientific results are constructed and how they are represented as objective knowledge, in particular by the means of visualization. His famous books include How Experiments End, Einstein's Clock and Poincaré's Maps, and Objectivity, co-authored by Lorraine Destin. Since 2016, he has co-established the Black Hole Initiative at Harvard, which also collaborates with the Global Event Horizon Telescope Initiative. Peter has won many awards for his work, and most recently he was awarded the Breakthrough Prize in Fundamental Physics. And yet, with all these accolades to his name, Peter Galison is by far the most multi-talented person I know. He is not only a scholar and academic, he has produced and directed 4 documentary films, the most recent being The Edge of All We Know, which also won awards. And he has collaborated with William Kentridge, a well-known South African multimedia artist, on several installations and projects, including signing for the dramaturgy, that's a difficult word, of a chamber opera called The Refusal of the Hour. So I would like to say there's really no one like him, and I'm personally delighted that Peter will be here virtually today with us to give this fourth 7 Pines public lecture. And I hope that you will join me in welcoming him by clicking the raise your hand button at your Zoom screen. With that, I'll hand the floor to Peter.
Hello, everybody. Thank you, Jos, for the gracious and generous introduction. Thank you for inviting me to give this public lecture. I'm only sorry we can't be together in the same place in real life. But we have some new results from the Event Horizon Telescope, which are going to be reported in DC on Thursday morning, and I need to be there for that. And so I'm happy to be able to join you, at least virtually, to tell you a little bit about the making of the black hole image and some of the conceptual issues that lie in back of it, both historically and epistemologically. I'm now going to share screen. Okay. The use of shadows. So Jos, could you raise your hand if you see the image correctly, if it's going out okay? Yeah, thank you. The use of shadows in astronomy goes back to distant antiquity, and in the late Renaissance was used by Galileo to great good effect in understanding, for example, how the irregularities in the terminator line between light and dark as we see the moon could be interpreted as to show the existence of valleys and mountains. And from the distance from the terminator line, he could calculate how high those mountains were and decide they were some 4 or 5 miles up from the surface of the moon, which made the moon much more like the Earth than had ever been suspected. Indeed, it was thought that the moon and above was perfect. And so demonstrating that there were mountains there was a serious blow to Aristotelian and neo-Aristotelian cosmology. In the black hole visualization problem, we are also using shadows. And the idea is that when you have a black hole, it so distorts the space and time that light from the surrounding hot gases and light that arrives from elsewhere in the universe are actually bent by the black hole. And the bending of that light occurs to light that comes from any which way. And eventually, when we look at the black hole, we see it essentially in silhouette. That shadow or silhouette of the black hole represents a way of understanding we can use it to calculate the size of the black hole and therefore what its mass must be, knowing the distance to it. Now you might say, what kind of image is this? Are we really seeing, when we see in the infrared, the frequency that we use, in the radio telescopes that we use are in the far infrared. And we use the infrared when you see a fox or a coyote go by with your critter cam. We don't have any doubt that we're seeing a fox or a coyote. So, and there's many images in the Museum of Modern Art's photography collection that are in fact based on infrared photography. So surely being infrared or not having radiation that's immediately visible to us is not disqualifying as a photograph or as a form of seeing. Now you might say, these images are intensely processed digitally. Well, so they are too in your cell phone. And when we take a picture or a selfie or a picture, we certainly consider ourselves to be taking a picture, taking a photograph. And although without the computational capabilities of the cell phone or the digital camera that you use, there would be no chance of producing the kind of image that we are used to today, since we no longer, in most of our photography, rely on film. In many instances, many types of film are no longer even manufactured. Now you might say, are we seeing when we see a silhouette? Well, Roger Deakins, one of my favorite cinematographers, certainly thinks you're seeing when you see scenes in his many films, when you see a soldier come off the horizon and you see a scene from of runners or threatening figures, or any of the myriad other ways that we see silhouettes. So I want to talk about shadows and the search for an objective image, the kind of image that the image of the black hole is. First, by discussing what objectivity in images are and how those have changed and accumulated over time. Second, by discussing in particular the black hole image of M87, the 55 million light year distant black hole at the center of a galaxy of the same name, and then discuss some of the philosophical aspects of this, both along the way and in conclusion. Now, in a kind of parodic or cartoon way, you could think of there being three strata or layers that have accumulated in how we understand image making, or the best representation in science. In the 18th century, it was considered to be absolutely necessary to idealize the images that we took. Now you might say, here's William Cheselden, 1733, using camera obscura to image this upside down skeleton, which is inverted in the device, and sketching it on top of a frosted glass frontispiece. But he's not. He says we need to fix with pencil, needle, and placement the imperfections in the skeleton. Nobody in the 18th century wanted some random person's cracked rib and misshapen vertebrae. They wanted the ideal form that lay behind those particulars. When Goethe talks about using the Urpflanz or the Uransicht, he says very explicitly, no particular animal can be used. We want to show the form behind the particulars. That was seen to be obvious in the 18th and early 19th century. Or when Albinus, one of the great anatomist artists of all history, depicted this skeleton, its idealization is evident, not just because skeletons don't normally dance in front of white rhinoceroses, but because he said we must mend those things which are less than perfect to exhibit a more perfect form. So continuing in our cartoon spirit, I would say that from 1730, dates exaggerated for conveyance of the sequence, you have a scientific self, which is a genius or a sage who's able to part the curtains of experience, so to speak, and see the form that lay behind it. The image itself has the status of representing, of being metaphysical. It's not about any physical object. It's about a form presupposed to exist behind any particulars. The practice is one of massive intervention, fixing by means of pencil or other device, that which was observed in particular, and the ontology of the thing represented was of a universal. In the mid-19th century, the first third to mid-19th century, you begin to see a radical departure from this ethics and epistemology of the image. People like Otto Funke in 1853 said, as he depicted the crystals of blood, he's known for showing how blood conveyed oxygen, that he knew perfectly well that one crystal in front of the other caused diffraction and caused refraction, and that refracted image was led to a distortion. Just like when you stick your arm in the bathtub, it looks bent at the water-air interface. So it is here. So it's too in the figure 2 on the right. If you look at the lower left quadrant, you see a yellowing. That's a chromatic aberration. That's entirely the product of not very good microscope lenses by today's standards. He knew those were not real. The chromatic aberration and the refraction of crystals in front of the other, but he drew them anyway because he said, my job is to be faithful and conscientious, to draw even the deceptions. So not only was he unwilling to abstract to a universal in back of the particulars, he wasn't willing even to correct the particulars to what he knew was the case, which was that these crystals didn't suddenly bend when one went behind the other, or a yellow blob appearing in the lower left quadrant here. He wanted to transform himself into a faithful and conscientious conveyance vehicle that would take us from nature through the microscope to the page. Rudolf Virchow in 1877 put this in a way that I find particularly compelling. He said, I am now among the oldest professors of medicine. I have been teaching for more than 30 years. I have honestly worked on myself to do away with ever more of my subjective being and to steer myself ever more into objective waters. Nonetheless, I must openly confess that it has not been possible for me to desubjectivize myself entirely. With each year, I recognize yet again that in those places where I thought myself wholly objective, I have still held on to a large element of subjective views, my opinions, my representations, my theory, my speculation. The goal was to divest himself, for us as scientists, to divest ourselves of these specificities of the observer. So continuing our cartoon characterization, you still have into the 19th century and indeed into the present ideas of idealized images. They still function. You can see them, and I'll give examples of that later. But you would begin in the 1830s to have a new layer laid on top of it, like a geological stratum, where the scientific self doesn't aspire to be a sage or genius, but instead a conscientious worker. You don't want somebody improvising in the fork machine or bullet machine. You want every bullet and every fork to come out in an identiform way. The image was one of mechanical transfer. It was mechanical in the sense of algorithmic or procedural, not simply the basic machines of mechanics. It could be chemical. The practice was one of mechanical transfer insofar as you could, and you might not ever be able to extirpate intervention completely, but insofar as you could, you wanted to set a set of procedures, whether it was tracing or copying mechanically or putting ink on a leaf and then pressing it onto the page, whatever it was, a procedural way of transferring from nature to the page. The ontology was then one of individuals. This continued, including to the present. You have atlases, these compendia of scientific images that characterize many different domains of science. When you get to the present, but in the beginning, around 1930, 1920, 30, 40, you begin to see another kind of intervention where people say, you need to use a certain subjectivity in representing things because the machines have quirks, idiosyncrasies that a trained expert would be able to recognize and extirpate. A certain subjectivity to these charts, said the authors, Howard and his colleagues, were necessary, for instance, to get an accurate depiction of the solar magnetic fields and to remove from them the artifacts that they knew from long experience were being put on the page by the machines. This is not a return to the genius or sage. These are people, you and I can become experts trained in the art. And when we do, we can learn to distinguish grand mal from petit mal seizures on electroencephalograms. We can learn to interpret all sorts of images and indeed to correct them when they need correcting. So one goes from a kind of sage to a conscientious worker to a trained expert. These are three sequences of image regimes that will prove important in what we will discuss in a moment. So in this more contemporary period, 1930 through the end of the 20th century, certainly the scientific self is one of a trained expert. You don't have to be born an expert, you can learn it. The image is one that's interpreted. It's not simply given either mechanically. It certainly doesn't stand for something metaphysical. The practice is one of conditioned judgment, trained or conditioned judgment. And the ontology is one of families, not individuals or universals. Okay. So put into a kind of timeline, I would say that the truth to nature, the idealization that begins in the 1730s, continues today. You can see them maybe without its metaphysical gloss in, say, a guide to birding, where you would see a bird with a red spot prominently displayed. This is used in teaching people how to read X-rays. You exaggerate a feature to facilitate recognition, classification, and understanding. Mechanical objectivity begins in the 1830s. And again, you can continue to see that used where one strives above all to remove the intervention by the author or person representing the natural phenomenon in order to allow nature to go to the page as protocol driven as possible. And then one has trained judgment beginning in the 1930s. I put it this way to emphasize that this is not a Foucauldian or Kuhnian picture in which one of these is suddenly disrupted, splintering science into blocks, but instead more aggregative. They interact with one another, they coexist, they're coeval in many cases, and we will see an example of that with the image of the black hole. Now, when we look for black holes, there are two kinds, grosso modo. They're stellar mass black holes that are the mass of the sun, or 10 or 30 or 50 times the mass of the sun. And those are formed typically from a star running out of energy, collapsing. It's the merger of such stellar black holes that LIGO, the great interferometric array of several stations that look at gravity waves as they drive enormous mirrors back and forth in a laser interferometric instrument. And then there are these enormous black holes, one of which seems to sit at the center of every galaxy. These supermassive black holes are millions or even billions of times the mass of the sun. In terrific work that was also, like LIGO, awarded the Nobel Prize, Andrea Ghez and Reinhard Genzel looked at the stars that orbit the center of the Milky Way. And these stars, have the quickest of them goes around in about 15 years, which for astronomers is astonishing. I mean, there are planets that take a lot longer than that to get around the sun. So that a star could be pulled around the center of the Milky Way galaxy is extraordinary. And they used those orbits to calculate the mass of what must be a compact, an unseen object at the center of the Milky Way. So this is a visual, but not very close in picture of what a black hole does. It's maybe 1,500 times the radius of a black hole, of that the Schwarzschild radius. And so it's visual, but not close in. LIGO, on the other hand, measures these black holes very close in until they actually come together and ring down and become one bigger black hole. And that's close in, but not image oriented. What the Event Horizon Telescope is after is to try to make a horizon scale, like right in near where the black hole is, image of a supermassive black hole. Now, to do that, you take an array of radio telescopes that look at radio frequencies that have a wavelength of about 1 millimeter, and you collect an enormous amount of data. Each night is over 1 petabyte of data is collected. Just for reference, a library like the Library of Congress, one of the libraries of record in the United States, has about 2 petabytes of data in it. So collecting on roughly the amount of the data that's in all of the books and magazines and ephemera in the Library of Congress every night. And so you can't set, you say, well, you could send them by, could you send that data by the internet? No, there's no chance you could come anywhere near being able to send it by the internet. Even if you could, one of the telescopes is in Greenland and one of them's in the South Pole. So it would be hopeless. We barely can get a telephone call to the South Pole. It's certainly not possible to send petabytes of data. So these blocks of specially designed hard drives that can function at the high altitudes where these radio telescopes live, and they're shipped back sometimes by Federal Express, sometimes in the belly of a military transport plane, sometimes carried back by people, and they're then put into a supercomputer, which correlates the measurements from the 8 telescopes that were running in 2017, distributed over 6 sites around the world. What you're trying to do is to simulate a telescope the size of the Earth itself to be able to blow up the tiny image of the hot gas around the black hole as seen from Earth. For the black hole in M87, it occupies an angular size on the sky about like an atom held at arm's length, or looking at a coin's date in Paris as seen from Minneapolis. So this is how that works. You have these instruments around the Earth, and the fundamental unit of analysis is the baseline. It's almost like each of these baselines connecting 2 different telescopes forms a kind of a tuning fork tuned to a certain frequency. And these, as the Earth turns, different of these telescopes, different pairs of these telescopes come into visibility of the black hole, and together they begin to cover, at least in a sparse way, the baselines cover the pseudo image, the synthetic aperture of an Earth-sized telescope. It's as if you had a giant mirror of a telescope where you only had a few pieces of that mirror, and you got the information from each of those, and then you sent it back to a supercomputer to try to reconstruct what that image was. Now, there's an interesting parallel that's deep, in fact, at a technical level, between the sparse sampling of this synthetic giant Earth-size radio telescope and what an MRI does when it peers into your body. Both of them measure frequencies in a sparse way, and then they're combined by a computer to make an image. To push the parallel a little bit farther, you have a black hole, you have a sensing system. In the case of the Event Horizon Telescope, a sequence of radio telescopes disported around the world. You cover a fraction of the frequency space, so to speak, like as if you had simply samples from of certain notes from a musical performance, and from it you were trying to reconstruct the whole symphony. And you used an algorithm to do that, and you get back the image. So it is with medical imaging. You have a sensing system, an MRI system. It captures these sparse samples of the visual frequencies. An algorithm recombines them and makes the image. So the first and most fundamental part of the reconstructing program that we have to engage in is that you have to take this sparse data and reconstruct it. That there's a kind of invisibility until you can interpolate into that sparseness and create the whole image. The problem is one that you might think of as underdetermination. That is to say, if I said to you, please separate the blue dots from the red dots, you would rightly say, what do you mean? Do you mean I should find the best circle that separates most of the blue dots from the red dots? Do you mean find the best ellipse that separates the blue dots from the red dots? Or do you mean like actually go in there with my green crayon and separate one by one the red from the blue? Now, in that sense, the answer to the question, can we separate the blue from the red, is simply underdetermined. There are many different ways of proceeding. What you need in order to make this a well-posed question is to say, what is your assumption? What do you want? What are the conditions under which you want that separation to take place? Best ellipse, best circle, exact differentiation. Those can be thought of as priors. They're the assumptions under which the task is conducted. This method for both medical imagery and finding black holes is often referred to as the regularized maximum likelihood. You have a true image here represented as a simulated black hole in the upper left. You have a sparse set of sampling stations. You have these radio telescopes around the world, but they're not everywhere around the world. If they were everywhere around the world, there'd be no problem. And then you get some data. Why? And you could say then, well, can we match that? The problem is, just like in the separating of the blue and the red, that there are many different image solutions that equally well fit this data. So what are you going to do? How are you going to separate, say, which of those 4 images in the 2x2 block at the lower left here is the right image? Well, what you do is you have to make some assumptions, like when I said we need to choose, get the best circle, get the best ellipse. What do you want? So we have some prior knowledge of what we might think the black hole image might be like. Like we expect that it's not completely diffuse, or that it might have some edges, or that it might be fairly compact. And those are the priors. Those are assumptions under which you could proceed. And if you impose some prior expectations on what the image ought to be like, then the problem becomes well posed, and you can find the best image that is most likely to, that has certain features that you believe are true of the true image and is consistent with the data. So now you're in business and you're cooking with the proverbial gas. And so you can begin on general grounds to classify some of the candidate images that do fit the raw data as unlikely, more likely, or very likely. Now, the converse problem arises. Like Narcissus looking at the spring and seeing only his own reflection, there's a worry that if we said, okay, we expect a donut-shaped image of a black hole, and we expect a bright arc in the south, and then the computer will say, okay, that's what you want. I'll find you the best donut-shaped image with a bright spot in the south, but you wouldn't have learned anything because it couldn't have been otherwise. So if you make your expectations too weak, you can't proceed. The problem is underdetermined. If you make them too strong, you get back what you put in, garbage in, garbage out. So how do we proceed? How do we convince ourselves? How do we sail between the Scylla and Charybdis of too little and too much expectation? Like, how do we convince ourselves that our pursuit is objective in this dangerous world of sparse data? So the first thing that we did is, maybe completely unsurprising to sociologists or to psychologists, we made up a bunch of groups, told them not to talk to each other, and sent out random test data, and then said to each of the groups, okay, take this thing that you're getting, this image, this whatever it's going to be, this data, and give us back the best image you can find. So here's an example of one of the hackathons. We took some simulated black hole images. We see where it says target. This is what the image was that was sent out. Although nobody was told, none of the members of these different teams were told what the image was, or even what category of image it was. Some of the images were astronomical, vaguely speaking, and blurred. And then some of them were just randomly plucked off the internet, like Mr. Photographer here. You see the actual image off the internet in the upper right. And then the target, once it was blurred, looks like the upper rightmost square. And then these different methods each tried to reconstruct it. And you can see, well, the chirp method, I can explain what that is later, but one of the methods seemed to get something like the blurred actual target. The other ones, and it didn't do so well. And we kept iterating this until the various groups got good enough at extracting an unknown image and reconstructing something a lot like what went into it. In a slightly perverse way, just to complicate things, one of the images that got sent out was Frosty the Snowman, just because nobody could have guessed that that was the image. You might have guessed it was going to be symmetric or astronomical or something, but Frosty the Snowman seemed sufficiently unexpectable, so to speak, that each of the teams had a real challenge in trying to reconstruct it. And as you can see from the lower bluish images here, quite a number of the methods found something like a slightly blurred Frosty the Snowman. So that was the first technique, this blind imaging. Here you see some of young colleagues putting up opaque paper on the seminar room so that the other groups, this was hiding not from espionage from some other place, but just from the other groups, so that nobody could try to imitate inadvertently or advertently what the other groups were finding. And after we got pretty good at recreating the various images that were sent out to in the blind group assessment, this is a scene taken from that I used in The Edge of All We Know in the group that I was part of, so-called Group 1. And this is the first time anyone's ever seen a black hole. And I'm going to just play you a few minutes of that.
For me, I'm not like, I'm just saying, like, I think it'd be fun for us all to do the first one together, see the shit, and then go off in our own little ways and fix it. I mean, I think it's just like, it's so exciting that do you want to do it alone?
I would like to see it all together so we can get some idea of the data.
Are you ready?
Ready?
I'm ready.
Ready? Is that gonna work at all?
I'm going to do enhance, enhance, enhance.
Ready?
Set. Go.
Go? Oh my god! Oh, look how we press go!
It's just a waffle. Ah, that looks really, really interesting. How's the waffling going?
Andrew looks beautiful, but there's no tweaking involved.
No. If I put compactness very high.
I think Daniel and I were both getting something like this.
Yeah. You know, okay.
Oh, that's what I get when I use only closure.
Only closure.
Oh my god, look at the chi-squares.
That's pretty good.
And coverage. And then this is, after a few more iterations, it smooths it out and gets rid of some of the extended junk.
This is on mobile? Or
Wait, but is this only one day?
This is only one bit.
You know what?
That's pretty suggestive.
Well, it seems...
Did you remove these outlines from the amplitude?
I didn't touch anything.
That is very cool, guys. That's really, really cool. Which one is that?
This is Katie's image.
So that was amazing. And then we had the other three teams. They also were getting similar shapes and forms. The color, I should say, is arbitrarily chosen. We can discuss how we chose the color, but the shape is not and the brightness is not. So we're all seeming to get some, southern brightness, black disk that corresponded to a black hole of about 6.5 billion solar masses, and a temperature somewhere around 1 billion to 10 billion degrees Kelvin. And blurring those images and combining them, we could look at them. On July 24th, 2018, we got the various groups together and saw that they, comparing them pixel by machine, and then looking at them, we could begin to see that these really, really did correspond to something very similar. So that was tremendously exciting, but we had another almost a year, 9 or 10 months before we are willing to go public with that, because we just were completely paranoid that we were making some stupid mistake, or that we were unconsciously adapting our methods to try to get something that looked like a simulated image. And so we began a next phase of things. Could all of our choices, all 4 groups, have been driven by a common set of theoretical expectations. That is to say, a set of expectations in common among the 4 groups. And to try to get at that, we used a form of mechanical objectivity. Instead of using just expert judgment, each group use just use everything you know and get the best recreation of these variety of test data back to a return image that looked that you would stand behind, and then we could compare them pixel by pixel with the target image. Now we wanted to do something completely different. Now we wanted to say, let's take the, what might be thought of as the analogy of a camera, and let the computer change the focal length, the speed of the film, the aperture opening, the time of exposure, all the different settings, and just change things around and see what worked best to create various simple geometrical forms and see where that got us. So for instance, one of the settings was how sharp the edges were between parts of the image, or how much total flux, how much total brightness there was in the image, and so on. So we said to the computer, you can change all these parameters as best you would like, and take a disk, change around the parameters until you get something that most resembles the disk, call those settings beta, and then take those settings beta and apply them to the real data from M87 and tell us what you get, show us what you get. And the computer returned an image like this. That's promising. We're not starting by assuming we have a donut. We're starting assuming we have a disk, and we still get a donut. That was promising. What about if we said to the computer, okay, computer, take a donut, take a crescent in the south, take a disk, take 2 separate blobs, and vary the parameters so that you get the best recreation of all 4 together. And so the computer grinds along, chooses a set of settings beta, and then we say to the computer, now take those settings that you got from getting the best reproduction of all 4 geometrical forms and try it on the real data from M87 and show us what you get. Again, a donut, bright crescent in the south. So that seems pretty promising. This is a method that involves no expert judgment. It says to the computer, you set the parameters to get the best image of a test image, just the way you might say, test a camera on a test pattern and adjust the lens and settings and so on until you get the best reproduction of the target shape on the wall. And then now you trust the camera when you point it at something you've never photographed before. The third stage, and there were some real hard discussions around this, said, okay, in our observation period in April of 2017, we had the best conditions. You want the weather to be good all over the globe. It's very demanding meteorological need. And so we took the April 11th data and we said, okay, look at these 3 different methods, and here's what you get using these mechanical objective forms. And then what should we average them? And when you average them together, you got this image, which became the canonical image that we showed. And then the argument really began. Do we want to show an average image? Some people said, no, whatever you do, don't show an average image, because the average image doesn't correspond to any data that was taken off the sky. It requires a manipulation, that is to say, an averaging over these different different pipelines. I don't know what ringing that is. It's not from my end. So this was a form of idealization. Averages, there were times historically when averages were thought to be a form of truth to nature. If you average, some people thought, the all the kidneys from some large number of corpses, you would find somehow the true or ideal weight of a kidney. This wasn't an assumption along those lines. It wasn't saying that the idealization afforded by averaging was of metaphysical, a piece of furniture in Plato's heaven, but instead that the average might have other advantages. And there were three arguments. I didn't like all of them, but here were the arguments. One was we should average because that would then include the wider collaboration of all three methods, or because that each of them would contribute to this composite image. Well, that seemed to me a kind of nice sociological feature. But if one of the images was better than the other, I think averaging them just for the sociality of it was probably not a good scientific idea. A second argument I thought was more promising, which was, so I'm just editorializing here about my view, not everybody shared these views. The collaboration includes people from several dozen countries, many dozen institutes. At the time, in 2019, there were some 200 people on the collaboration. Now there's some 300. So it's grown a lot. But for instance, if you tested the average and said, is the average like each of the constitutive images that made it? That actually is important. For instance, if I said, average a Mount Everest picture with a picture of a hole in the ground 5 miles deep, the average would be, say the Mojave Desert, but nice flat image like that doesn't look at all like Mount Everest and doesn't look at all like the 5 mile hole in the ground. So the fact that the average image actually looked a lot like the constitutive three images seemed like a good test. But the best argument seemed to me that it was a conservative approach. That is to say, it said that by averaging these images, we are emphasizing the features that are held in common because they show up on all, and so they survive the averaging. Whereas if some feature, some fluffy part of the image out in the far part of the image was only present on one, then averaging it would tend to reduce it and make it much less salient. So the average image is in a sense saying, what does everybody agree on? What are all the images? Where's the consensus image? I mean that in the sense of a consensus among images, not a vote among people. And in that sense, I thought that was probably a good argument for averaging. And there were other arguments, for instance, if different publications, it was pretty clear this was going to be a very widely distributed image. In fact, 1 billion people saw the image within 24 hours of its release. We didn't want to have like ones that differed from each other because then people would wonder what relationship they had, and it would create a lot of difficulty of interpretation. So in a sense, what we have here is the opposite of history. That is to say, the historical image went from idealization, Goethe, Albinus, Cheselden, to mechanical objectivity, the kind of Virkov style desire to make protocol and algorithmic approaches sort of transfer nature to the page with as little intervention as possible. And then eventually to trained expertise. What we did was essentially invert that, keeping all three. We started with a trained expertise and then went to mechanical objectivity, where we had the computer cycle over all the different combinations of parametric choices, and then to the consensus image where we were averaging, which was a form, in the sense, of idealization. So with that in hand, on the 10th of April, 2019 at 9:07 a.m. all over the world, people, we agreed we would show the image. And this is from the Washington, D.C. presentation, but there were similar ones in many, many other cities. So that was a great moment. I mean, just to fix ideas, the dark area, the black hole of M87 is about 20 billion miles across, which is about 3 times the diameter of the solar system. This is an enormous black hole. And And then, you know, in all of this excitement, I had my own misfortune. I started feeling worse and worse, and x-rays showed nothing. I wandered from emergency room to emergency room, and finally, in somewhat desperate straits, a doctor at a very good hospital near here said, let's get an MRI. And on the MRI, a technology that I trusted because I knew about, my teacher Purcell, you know, was one of the co-inventors of nuclear magnetic resonance, and I regularized maximum likelihood method and all these other techniques that we were using really had their parallel there. And I thought, good, an MRI. And indeed, the MRI showed very dramatically what was wrong. I had a massive spinal infection, which was thinking of doing me in. So it saved my life, and I thought that was somehow a kind of poetic justice that this same technology was both helping to reveal what was about to kill me and some of the more exciting moments of my academic life. So now then, you might go back to Galileo. And what did Galileo do right around the time he was looking at the fluctuations in the terminator line? He started to write down pictures day by day of Jupiter and these wandering stars that were next to it. This is January 1610. Essentially what he's doing is making movie frames of the Medicean stars, or what we call the moons of Jupiter. And you could take them, these are from his original drawing, but simply made into a GIF, and you see you have a kind of movie. This was incredibly important because once he could see that these moons were orbiting around Jupiter, once the Medicean stars were known to go around Jupiter, they would have crashed through the crystalline spheres had there been Aristotelian crystalline spheres. So again, this was a blow against traditional cosmology. And so it is with the black hole. One of the things down the line that we would like to do is to be able to use to improve the array to the point where we have enough data to actually see movies of hotspots orbiting the black hole, movies of things falling into the black hole, across the horizon and disappearing, flares like solar flares, only much bigger, that flash out from the accretion disk around a black hole. And so there's much still to do. There's more targets to look at. There are many other black holes to explore. There's movies to be made, and imaging is a way to do it. Imaging is a way of sort of seeing the unexpected, to be open to new possibilities. And it's that which will keep the Event Horizon Telescope and the next generation of the Event Horizon Telescope busy for quite some time. And with that story of the image of the black hole, I'll take.
Okay, thank you very much, Peter. We have time for some questions. And if anybody in the audience wants to raise a question, you can either use the Q&A box, and then I will read the question posed there to the rest of us, or you could raise your hand and then unmute yourself and ask your question yourself. So I see a couple of questions already arriving in the Q&A box. And the first question from an anonymous attendee is, what happens if the prior assumptions are incorrect? And this
Okay, let me, yes, I can see these. So let me just address a couple of them in order. Some of the prior assumptions are 100% certainly incorrect. For instance, we tried a disk, we tried a ring, we tried two blobs. You don't want the prior assumptions to be too determinative. If you only use the correct prior assumptions, and that's the only way to get the answer, you're in a sense not being open enough to new possibilities. So now, if the prior assumptions are, if you're very demanding of a wildly off prior assumption, you'll also get nonsense. So there's a compromise that has to be made between, plausibility, but not assuming exactly what you want to see. And that's sort of the conundrum here. You want the image to be open to things that you didn't assume, but if you are completely open, the question is underdetermined. You simply don't have any way of separating the blue dots from the red dots, so to speak. What was considered the real data from M87? Well, it's a good question. We had this data that we'd taken in April of 2017 over the course of 5 observing days, and the 8 telescopes on 6 sites each captured data that they were seeing. Those were then fed into a supercomputer, one of them in Massachusetts and one of them in Germany, and they line up the different results to try to get the timing exactly right to within a wavelength of each other. And then that aligned data, the correlated data, then becomes the base data for all of this analysis. Tom B asks, would a black hole appear regardless? So that's a very good question. You might think, for example, of the black hole, if the hot gases are roughly symmetrical around the black hole, then yes, it'll look the same from all directions. If you have a plane of accretion, like, say, the rings of Saturn or the planets around the sun that are basically in a plane, then it'll look somewhat different. And under certain circumstances, it'll look more like the image that you saw in the movie Interstellar, which were the simulations there were directed by Kip Thorne, a great astrophysicist who runs a hugely sophisticated digital project to simulate these things, and they supervised the making of those images. Elizabeth Butler says, find the image that best approximates the original. How do you determine best? So that's a good question. So for example, in the case of a static image, if you start out with a disk and it's got a certain size, then you could say the computer will try out various things, and some of the parameters might dig a hole in the middle of it. Some of them will flatten it out or make it asymmetric. Some of them will return the wrong size. And so the comparison is pixel by pixel. You look at the correlation of the reconstructed image and the original image. For synthetic data, you have the original image. For the black hole, you don't. So the idea is test it on things where you put in, like taking your camera and looking at a test pattern on the wall. You know what the test pattern really looks like. You develop the film, you get the image, and you compare the image that the camera took to the pattern that's taped to the wall. And that, you could compare it pixel by pixel and score it. That's what we mean by the best. Sophia Osofsky says, how do you get involved with doing research like this? Well, we always need more people involved in radio astronomy. And if you're interested in this kind of work, the combination of astronomy courses and physics courses is probably the best path to that. If you're interested in following it, we hope to have lots of explanatory little videos, more and more. We're making more and more of those that will be up for people who are not expert to be able to follow the way some of these arguments work. Doug Plunkett says, what was the total length of time from project conception until release of the first image? That's a really good question. It kind of depends on how you count the beginning of the project, but somebody like Shep Doleman, who was the director of the project up through 2019, and I'd say he spent 15 years. And in the beginning there was just a handful of people working on it. I think when I joined in 2015, 2016, there were maybe 50. By 2019, there were 200, and there are now 300 people on it. It requires people from all sorts of different expert backgrounds. There are computer vision people. There are experts on, fixing giant radio telescopes. There are theorists. There are experts on imaging. I mean, there's lots of, it really does take a village. Ray Peterson asks, how many CPU hours required to synthesize the final image from the raw data? Okay, well, that's an interesting question too. So we start with petabytes of data, then you correlate, and you get, you get down to gigabytes, and then by the time we actually make an image, they're kilobytes of data. They're very small, and we actually then build it back up when we want to blow it up to a big size by interpolating among the pixels. But the actual final data is quite small. So the big computational problem, there are two of them. One of them is simulating what we might see, because you want to have some notion, you want to test your programs against simulated recreations of black holes. And that requires basically the biggest, most massive supercomputers that you can muster. The other place is in this correlation. And that's going to get harder and harder, because right now, what we're doing is we're adding telescopes to try to fill in some of that sparsity. And so we had 8 telescopes. I say 8 telescopes. Some of those 8 are actually arrays of telescopes. So it's an array, in some cases, of arrays. But like the great array in Chile called ALMA, ALMA, and the correlation work that brings together this massive amount of data into an alignment rigorous enough to actually act like you have as if you had a surface of individual millimeter accurate surface. That's a huge computational problem. And now one of the things that we're starting to explore is using GPU, game processing units, instead of CPUs. So the answer to the question in number of CPU hours sort of depends on which part of the project, whether it's simulation or correlation or all the other manipulations that have to go down. Sometimes it would, we'd have to run a simulation on a mainframe computer for a week to get the kind of simulated data that we needed. Mr. Zhang says, Hushan Zhang says, I would like to ask if the computer test, which is said to be mechanical, contains trained expertise of people. So what we're trying to avoid in the mechanical approach of mechanical objectivity is people adjusting things to, in a way that would make choices that would advantage what they might prejudicially expect to see. And so if something, even if it was the case that there was expertise, as there surely was, in the design of a computer, the computer itself is tested in certain mechanical ways, calculating known quantities, for instance, that make sure that the computer is working properly. So the goal was to avoid putting interpretation in the driver's seat of reducing the image. And in that sense, having these various parameters varied. Sometimes we made millions of variations. The computer did millions of these different combinations. You can never explore all of the parameter spaces. Just there are too many possibilities, too many things you could vary. But we tried to sample very widely to see if the resulting image was robust. Nick Tavani says, how are the colors chosen? Can LIGO data be made into an accurate visual? What about a composite image from all modes? So we had a big debate about the colors. So for instance, some people said, so the brightness and the shape of the image are fixed by the data, the relative brightness, for instance, of the north and the south, or the east and the west. But the color is not determined. We can't see in the far infrared, so we have to decide how. We could have made it black and white, could have made it day glow pink. We came down to blue and orange, and some people said, look, the hottest part of a flame is the blue, not the red part. So maybe we should make this a blue image. But then, we talked about this, and I said, well, you don't put a blue warning sign on a stove and a red sign on a refrigerator saying how cold it gets. We tend to use cold and blue seem to be associated in everyday life. That was an arbitrary an aesthetic decision, maybe not arbitrary, but it was deeply aesthetic. Can the LIGO data be made into an accurate visual? You can make images based on the LIGO data, but it's not uniquely determined. Can you combine the various modes? Well, we did combine the various modes in the composite image. Maybe the question was, can we combine the LIGO data and the Event Horizon Telescope data? You can't, because there are two very different kinds of black holes. One of them is tens of solar masses, the other is billions of solar masses. I'm not sure which of those interpreted. So now, is the bright southern horizon unique to this particular black hole, the angle we happen to be viewing the item? So the interpretation of the southern brightness is partially, but not completely understood. The partial part is it's no doubt the Doppler effect, like a police car coming towards you and the frequency goes up and goes away from you, goes down. In light, there's something analogous to that. And so it's no doubt a Doppler effect, but exactly what the dynamics of the plasma are such that that's brightening there is still something that will only be resolved by more detailed observation. We're learning more about it by looking at polarized light, but still there's much to be learned. Could the various imaging teams and computer-generated images be described as generating a kind of robustness analysis? Yes, a lot of what we were doing was saying vary X and see if the image survives it. Change the parameters, change the priors, change the method of analysis, and see if you still kept getting that. So yes, I would say that it is a form of robustness. Why not take a picture of the black hole at the center of the Milky Way instead? Well, that's a good question. More to come. Isaiah Clark, how did you decide the color? Oh, so that has to do with that orange and blue question that I mentioned before. Will it be possible to make a movie of a spinning black hole? How can you tell it's spinning? That's a really good question too. Back in 1909, an astronomer named Curtis, I don't know his first name, saw that there were enormous jets or lines, features, linear features on the sky that seemed to be associated with this galaxy, M87. And the interpretation was not there for many, many decades. But the best understanding of what that is that a spinning black hole pulls space around it, so to speak, that's what it is to be spinning. And that spinning space curls the magnetic field lines into helices coming out of the north and south poles, so to speak. Those helical magnetic fields then pull up the charged particles, which emit light as they're accelerated. And we see those hot gases that are shot out the distances of many galaxies. Now, that's evidence of spinning, but not a measure of spinning. And one of the great and most interesting questions about black holes is, can we measure how close to their maximum, relativistically limited spin do they have? So that's why I say it's a really important question, because we really would like to be able to know, how much is, if there's a black hole at the center of our galaxy, the Milky Way, how much is it spinning? What's the spin of the black hole M87? And eventually go to other galaxies, to look at other galaxies and try to determine their spins. Some people think that most of them will turn out to be spinning near the maximum relativistically allowed. That's something would be really great to know. And there are ways that we're starting to think about that. Black holes cause light to go into orbit around them, not that just the gas is going around, but light itself can form these rings, these photon rings. And it could be that by looking at those photon rings, we could actually use it as a measure of spin. That would be fantastically interesting. If atomic computers were to be created, how would this affect the efficiency and time it would take to go through the data and image a black hole? If you could make a quantum computer that really could, at scale, make computations, it would be a huge boon. I mean, I think that's probably a pretty long way in the future, but yes, a quantum computer would be great to have for some of these really tough problems. In the more approximate term, I'm hoping that we could use these game chips, these GPUs, to hugely accelerate this. I see Jim Weatherall has a question. Jos.
Yeah. Jim, can you unmute yourself?
Or Jim, if you could type it in, I'm not hearing you.
Sorry, I think I just misclicked something. I'm listening in while driving my daughter home from
Okay,
dance class.
so you're not trying to ask a question.
No, I'm not. I'm sorry.
Oh,
Hello, glad to hear your voice in any case. I don't see any more questions. Are there open questions there?
I don't see any either. But I think you've done a great job in answering all the questions that were there. And so I would propose to bring this to a close, and thank you once again for this wonderful and exciting talk. And I would like to encourage all the participants to follow the news about the press conference that's going to happen tomorrow.
Thursday, yeah.
Yeah, and
Thursday.
the first day. And so we'll hope to learn more about black holes from the Black Hole Initiative and the Event Horizon Telescope. So,
And I
Peter,
want to thank you, Jos, and thank the Center for Philosophy of Science and Seven Pines, and thank the incredibly interesting and terrific questions that people have posed. I appreciate that.
yes, so do I. So thank you all for listening and watching this talk, and we'll hope to see you back on the next 7 Pines public lecture, which will probably be in a year or so. Thanks, everyone.
Thank you all. Bye.